Good morning, everyone, and thank you for being here. My name is Muhammad Hafizi bin Muhammad FAZLI. Before we look at the map and the curve on my screen, I want you to imagine a commercial plantation manager in Sabah or Johor. Every single morning, they look at 1,000 of acres of oil palm trees and have to make a multi-million ringgit decisions. Is today the day we harvest or do we wait? If they guess wrong, the financial loss is staggering. This is why we built this interactive platform. Today, I'm going to show you how we can use standard calculus, specially detective and rate of changes, to take the guesswork out of farming and pinpoint to exact day a fruit bunch is ready for harvest. Okay, look now. Let's talk about the biology of the Tenera. Hybrid fruit bunch. The life cycle of an oil palm fruit follows a very specific biological timeline measured in weeks after anthesis, or WAA, which simply means the number of weeks after the flower opens. Inside the fruit flesh, or the mucoscript, oil doesn't just appear overnight. It builds up slowly at first, then rapidly accelerate and finally flatten out. This creates a high-stake biological dilemma of planter. Dear early danger, if you harvest too early, say around 12 to 14 weeks, the plant cells are still storing water and carbohydrate. They haven't completed a process called lipogenesis, which is the conversion of sugar into oil. Your oil yield will be terribly low. The late danger how the danger on the flip side, if you wait too long, the fruit become overripe and detached from the bunch. When it hits the ground, international enzymes wake up and start breaking down the high quality lipids into free fatty acid or FFA. If the FFA level tick past 5.0%, commercial refiners will reject the oil of heavily penalized. So, our biological problem is finding that absolute sweet spot when oil is at the maximum but it hasn't started. Okay. Why is the crucial that we study this using data rather than just relying on human oversight? First, it's about national economic impact. In Malaysia, palm oil is a primary economic driver. A mere 1% or 2% drop in the national oil extraction rate due to poor harvest timing can mean hundreds of millions of ringgit lost at the milling level. Second, it's about sustainability standard. Under the Malaysia Sustainable Palm Oil (MSPO) framework and MS 2095 and 2014 standard oil industry is moving toward precision agriculture. We want to eliminate food waste to the source and optimize meal logistics. By using a mathematical model, we create a standard objective baseline that any plantation work can follow regardless of their personal experience. Now, let's turn our attention to the leaf simulator on the screen. Let's pretend we are field agronomists adjusting this data. In real time, setting the scale on the left, we have three parameters. The max oil yield is set to 18%, which is the genetic ceiling for healthy Tenere palm. The maturation rate control how fast the fruit ripens. If we have a great season with the lots of sunshine and nitrogen fertilizer, this rate increase make our curve steeper. Clicking by the yearly phase, click around 11 WAA on the graph. If I click the right, we have week 11 look at the pop-up matrix. The cumulative oil is low, but more importantly, look at the international accumulation rate. The descriptive is flat. This tells us the biological of factory inside the fruit hasn't fully turned on yet. Clicking at the spin phase at 70 WAA on the surface part. Now, look what happened when I click right here at week 70. This is inflection point in calculus. This inflection point in the calculus is where the second descriptive changes sign, meaning the first descriptive of front of growth reaches its absolute peak. At this exact week, the fruit is working at maximum biological speed, packing oil into the cells faster than any other time in its life. Finally, let's linear week 21. Notice how the cumulative oil curve has flattened out. The first detective is dropping down towards zero. This means the fruit is full, it has maximum its genetic potential. This is our perfect harvest window. Harvesting right here give me the meal maximum oil weight before the fruit drop and spoils. One way to make the HTML better. This website does an amazing job of showing the math behind melody. However, to make this HTML platform even better for real world industry, use my recommendation to is the integrate a dynamic FFRIC adjustment warning system directly onto the graph. Right now, the graph on show in the positive side how I accommodative. It doesn't show it the negative consequence of waiting too long. If we could overlay a synchronous amber and red line that starts peaking and sharply upward after week 21, it could visually represent the rising level of free fatty acid. Additionally, we could add a small calculator widget at the bottom. We can a manager input the current market price of crude palm oil, and the web page automatically display the estimated final penalty if they delay the harvest. This would they transform a great educational tool into a powerful financial dashboard. In conclusion, calculus is just an as abstract subjects meant for the textbook and a tool that can guide sustainable agriculture. By analyzing the rate of change in algae's greenhouse, we can protect our yields, boost our economy, and reduce agricultural waste. So thank you so much for your time and attention.
Okay, good morning everyone. My name is Nurul Shazwani binti Azhari and my number battery is F25B1670. Today I will present an interactive HTML project about tempoyak fermentation. A traditional Malaysian fermented food made from durian pulp. The bioscience problem being studied is how lactic acid concentration change during fermentation and how quickly it accumulates over time. During the fermentation process, naturally occurring lactic acid bacteria convert sugar into lactic acid. This acid lower the pH, prevent the growth to harmful microorganisms and give tempoyak its sour taste. To understand this process, the HTML uses a logistic growth function and its derivative to model lactic acid production and determine the instantaneous rate of acid accumulation during fermentation. Okay. Studying this bioscience problem is important because it helps improve the quality and safety of fermented food products. By knowing the exact rate of lactic acid production, agro product engineer can determine the best fermentation period, maintain product quality and consistency, scale up production for industrial use, ensure food safety by controlling microbial growth. According to the HTML, the optimal harvesting and packaging period is usually between day 3 and day 5 of fermentation. Therefore, understanding fermentation kinetic is essential for both research and commercial production. Okay, next, so this is mathematical modeling that we use for the tempoyak fermentation. As you guys can see, we model lactic accumulation using a classical logistic growth function. So the total lactic acid concentration, this one, and derivative rate of acid accumulation, this. Okay. Next, when I click on max acidity L, it represents the maximum lactic acid concentration that can be reached during fermentation. In this model, the default value is 1.8%, so I can adjust it to 2.3%. So the graph was going change. So next, so a higher value means the final product can achieve greater acidity. This parameter depends on factors such as nutrient availability and durian composition. So next is kinetic rate. This parameter describes how quickly lactic acid bacteria produce lactic acid. The value is 1.2. If the value increase, fermentation become faster. Factors such as temperature and bacterial activity can affect this parameter. For the peak bioactivity day, represented by T0, is the day when fermentation reach its maximum rate. The default value is day 3. At this point, the bacteria are most active and lactic acid is being produced at a faster rate. So, um, and, the graph display two curves. For FT, total lactic acid concentration, and the second rate of lactic acid accumulation. When I click over here, when I click on any point in the graph, the HTML calculates the exact lactic acid concentration and its rate of change at the specific time. This helps users visualize fermentation dynamic in real time. Okay. So the lactic acid concentration is 0.19%. For the derivative value is 0.540% per day. This indicates that fermentation is occurring at its higher rate during the logarithmic growth phase of the bacteria. One improvement will be to add a pH prediction graph alongside the lactic acid graph. Since lactic acid production directly affects pH, displaying both parameters simultaneously will help users better understand the relationship between microbial activity, acidity, and food preservation. This will make the HTML more educational and provide a more complete understanding of the fermentation process. In conclusion, this HTML successfully demonstrate how mathematical modeling and derivative can be applied to study tempoyak fermentation. It helps users understand lactic production, fermentation kinetic, and their importance in agro product technology. Okay, that's all from me. Thank you.
So good morning, everyone. Today I want to show you how abstract calculus directly addresses one of Southeast Asia's most economic engines, which is the oil palm agriculture. Oil palm is a cornerstone of global food security and bioenergy, but traditional plantation does not work as it relies on guesswork. So this web page bridges the gap between pure mathematics and field agronomy. Let us start with the core bioscience problem. Fresh fruit bunch, or the FFB, the fresh fruit bunch, does not grow at a constant speed. From the moment it flowers to the day it is harvested, 24 weeks later, its weight accumulation follows a highly complex, non-linear pathway. Why this studying why studying this specific trajectory is critical? In traditional farming, resources like water and expensive fertilizers are applied on a rigid, uniform calendar schedule. It is inefficient. If you under-fertilize when the plant is aggressively building tissue, your yield will drop and threaten the food supply chain. When we over-fertilize when the plant is stagnant, the nutrients will wash away into the river, which can cause environmental degradation and financial waste. To model this biological behavior, the tool uses a logistic growth function. Nature has limits, and a fruit bunch cannot grow infinitely. This is the equation that we use. So there are which we can break down the constants. The number 25 represent the biological carrying capacity, the absolute maximum weight in kilograms this bunch can reach. The 0.4 is the growth rate constant, and 12 is the exact midpoint weight. But static weight isn't enough. We need to find the speed of growth. By applying the calculus chain rule, the application computes the first derivative. This derivative gives us the exact kilograms gain per week. This mathematical breakthrough let agronomists move from looking at what the crop is to predicting what the crop needs. So in real life function, when the user clicks a different point along this curve, the app calculates the exact state of the fruit bunch. First is the during the week 0 to week 4, where the growth rate is near 0. So the biomass is incredibly low and the growth rate is near 0. This bunch is merely establishing a cellular structure. Extra fertilizer here is entirely wasted. Next, on the week 12, this is the mathematical inflection point. Here, the cumulative weight hits roughly 12.5 kilograms. But more importantly, the growth rate is at its peak at 2.8 kilograms per week. This represents the rapid bulking phase. This is the golden window. The tree is working at maximum biological capacity and demands peak water and nutrient support. Finally, at week 20 until 24, the growth rate drops back down to 0 and the biomass line flattens out, approaching its 25 kilogram ceiling. The bunch is now simply maturing its oil quality, signaling to farmers that the harvest window is officially open. While the underlying science of this tool is phenomenal, the current technical implementation has a major bottleneck. The web page currently relies on static HTML image coordinates to handle user clicks. If someone were to open this on a smartphone or a tablet, the image will scale down and the click coordinates misalign, and the interactive simulator breaks completely. My recommendation to improve this is to integrate a modern open source JavaScript charting library like Apex Charts. By replacing a static image with an entirely responsive canvas, the data points will become fluid. Users will be able to hover any exact pixel on any device size, ensuring flawless data accuracy, interactive 2D redux, and a better user experience. That's it. Thank you.